This is your presenter, Asloob Mudassar, and I am presenting slide number 2 of the course on atomic and molecular physics. In the today's lecture, I shall be covering Rutherford model, Bohr's model, correspondence principle, calculation of Rydberg constant, calculation of orbital radius of the electron in a hydrogen atom, and calculation of the angular momentum of the electron. Rutherford model. You see that in all the models, that is, for example, in the Rutherford model and in the Bohr's model, the spectral lines, that is the observed spectrum or the absorption spectrum of the stellar objects, that is the absorption spectrum of the hydrogen atom from the stellar objects. You obtain a spectrum and you then analyze those spectra very carefully and try to model the atomic structure. So the spectral lines help you to model atomic structures. So this is the key point. That is, the atomic structure is evolved through the analysis of the spectral lines obtained from the absorption spectrum of the atomic hydrogen obtained from stellar objects. So now I am going to present the Rutherford model. Different models were suggested to explain the relationship between atomic structure and the spectral lines. Most successful model was by Bohr in the year 1913. Rutherford postulates. So these are the Rutherford postulates that I am going to present. The number one is electrons move around the nucleus in circular orbits of radius r and velocity v, where r can take any value. So you see that according to the Rutherford model, the electron in an orbit can take any value. So it can be at anywhere from the nucleus. So, and electron when change its orbit, the radius r is a continuous parameter. So here r can take any value for the or when the electron in a hydrogen atom change its position, it can continuously change. That is, the r will change continuously. That is, the any value of r will be possible. The second point is that a dynamic equilibrium between the centrifugal force and the Coulomb force, that is the Coulomb force between the electron and the nucleus, exists. So there is a dynamic equilibrium, that is, while the electron is revolving in circular orbits around the nucleus, there is a dynamic equilibrium, that is the centrifugal force will be balanced by the Coulomb force. So centrifugal force will be repulsive force and the Coulomb force will be attractive force between the nucleus and the electron. So let's calculate the centrifugal force, which is very simple. So F with a subscript C is equal to m naught v square over r. So you can represent V as a function or as a product of r omega, and then finally you will get Fc, that is the centrifugal force, is equal to m naught r into omega square. So this forms equation number 2.1. And the Coulomb force, which is the force between the two charges, that is between the positive, that is between the proton and the electron, because we are considering the hydrogen atom. So we have the Coulomb force, which is 1 over 4 pi epsilon naught multiplied by the product of two charges, that is E, that is plus E due to proton and minus E due to electron, divided by the square of the radius between them, which is r. So this is the Coulomb force represented by a subscript with capital C. Whereas in calculating the centrifugal force, we have used small c as a subscript, and in the Coulomb force we have used capital C as a subscript. So you see that simplifying this equation, we have a minus E square over 4 pi epsilon naught times r square, forming equation number 2.2 as the Coulomb force between the electron and the nucleus. So under the dynamic equilibrium condition, the magnitudes of the two forces must be equal to each other. So we have this the Coulomb force on the left hand side and the centrifugal force on the left hand side, as in equation number 2.3. So these equations have been, forces have been written in their magnitude forms. Now solving this equation for the parameter r, which will be used later we get. So we can solve this equality in equation number 2.3 for the value of r, and the value of r is given by, which is r cube is equal to e square over 4 pi epsilon naught multiplied by 1 over m naught omega square. So here we need to find out the value of r. So taking the cube root of on both sides, we have r is equal to 1 over 4 pi epsilon naught raised to the power 1 over 3 and e square over m naught omega square raised to the power 1 over 3. So this forms the equation number 2.4. You see that here the value of r depends upon the value of frequency omega of the oscillations. The rest of the quantities are fixed. For example, the charge of the electron is fixed, the m naught is the mass of the electron is fixed, and the other parameters are also fixed. So here it means that r can take any value depending upon the value of omega. So if omega changes continuously, then it means that the r will change continuously. So now we shall work out that whether omega is a continuous function, that is the omega will be a continuous parameter, or it will be a discrete parameter according to the Rutherford model, and what will happen to the omega value according to the Bohr model. So first of all, we shall be talking about the Rutherford model. The total energy of an orbiting electron is actually the sum of the kinetic energy and the potential energy, and is given by equation number 2.5. That is E written on the left hand side is actually the total energy of the electron, which is equal to the E kinetic plus E potential. So the sum of these two energies will form the total energy of the electron. Now the kinetic energy is given by the expression, that is E kinetic is equal to half m naught v square. We can again substitute v by r omega, and then we can write the total kinetic energy of the electron to be equal to half times m naught times r square times omega square, as shown in equation number 2.6. E potential, that is the potential energy, will be equal to the work done on the electron in bringing it close to the nucleus at a distance r from infinity. So you see that you bring the electron from infinity and bring the electron from infinity closer to the nucleus at a distance r. So since you are bringing the electron from the infinity, so E potential will be equal, so energy will be stored in the electron as the potential energy, which is given by E potential is equal to the integral from infinity to r. And then you have this potential force due to the, this is the Coulomb force, that is the mod of the Coulomb force, and dr is actually the derivative, is actually the parameter with the integral parameter. So we have the integral from from infinity to plus infinity, and then I have substituted the mod value of Fc, which is equal to that is the Coulomb force, is equal to E square over 4 pi epsilon naught into r square. So here I am using the dummy variable r prime, and dr is also changed with the dr prime, because in the integral these will not matter. So after performing the integral, you will get this one equal to minus E square over 4 pi epsilon naught r. So this is the equation number 2.7, then give you the potential energy of the electron, and 2.6 gives you the kinetic energy of the electron. So E potential is negative as the electron is bound to the nucleus, and this will make the total energy E of the electron to be a negative quantity, and the total energy may then be regarded as the binding energy of the electron. And when the potential energy is zero, that is when E pot is equal to zero, it means that the electron has been ionized and it is outside the nucleus as a free electron. So now let's calculate the total energy of the electron. That is, we are using equation number 2.5 to calculate the total energy of electron, and the E kinetic and E potential has been calculated as shown in equation number 2.6 and 2.7. So substituting 2.6 and 2.7 in equation number 2.5, I get this relationship, that is capital E, that is the total energy of the electron, is equal to half m naught r square omega square plus minus E square over 4 by epsilon naught r. So this is the sum of these two energies, that is the kinetic energy and the potential energy. So you see that I have taken r common from this one, and then I have in the parentheses m naught r omega square. So one R I have taken common outside this parenthesis, and the other quantity is that, so this plus sign will be changed by the negative sign. So we have a minus E square over 4 pi epsilon naught times R. So now you see that I have so I have used equation number 2.3, which is, where is equation number 2.3? This is equation number 2.3. So from equation number 2.3, you can substitute m naught r omega square by its value, which is E square over 4 pi epsilon naught r square. So making this substitution, that using equation number 2.3, I have this expression. So this is the quantity that I have used from equation number 2.3, which is shown in the red color. So I have half r times E square over 4 pi epsilon naught r square, and the term due to the potential energy is minus E square over 4 pi epsilon naught r. You can see that the term in parentheses and the potential energy term both are equal, both are equal to each other when you multiply this r when r square in the parentheses, one of the r will be cancelled by the r outside that one. So then, of course, these two terms will be equal to each other. One term will be half of the second term, so the difference will be minus half. So minus half into E square over 4 pi epsilon naught r is actually the total energy of the electron in the Rutherford atomic model. So here I can represent 1 over r as a separate quantity, as shown over here. So I have shown 1 over r as a separate quantity because I wanted to replace the value of r by using equation number 2.4. So let me show you equation number 2.4. This is equation number 2.4, where I have obtained the value of r. This is the expression for the value of r, and I am using this expression of r in equation number over here. So you see that the value shown in red is actually the value of r taken from equation number 2.4. So you see that after simplification, these are the simplification steps, and the final result is total energy is equal to minus half times 1 over 4 pi over epsilon naught raised to the power 2 by 3, and E square m naught omega square raised to the power 1 over 3, as shown in equation number 2.8. So 2.8 gives you the total energy of the electron. According to equation 2.4, so let me show you equation number 2.4 once again. So this is equation number 2.4. So according to equation number 2.4, any value of r is possible. And so the electron is associated with any value of energy. So you see that if any value of r is possible, then from this expression, that is from the first line, if any value of r is possible, that it means that any value of energy is also possible. So if r is changing continuously, then it means that the total energy of the electron will also change continuously. So according to equation number 2.5, any value of r is possible, and so the electron is associated with any value of energy. Classically speaking, the electron being an accelerated charge particle in circular orbits, when it changes the circular orbits, will radiate electromagnetic waves, losing energy continuously in unstable orbits, and will spiral into the nucleus ultimately. That is, the electron will release energy in a continuous fashion when changing its orbit. So you see that here we have obtained through the Rutherford model, that is the energy of the electron when it changes its orbit will radiate continuously energy, that is will radiate continuous electromagnetic waves. And then the electron will have also a continuous energy. According to equation number 2.8, that is this equation, according to equation number 2.8, the total energy capital E depends on omega. Classically, the electron, while spiraling around the nucleus, would emit a continuous range of frequencies. So you see that when the electron will emit continuous range of frequencies, that is omega is a continuous parameter, then it means that the total energy of the electron will in the Rutherford orbit will also be a continuous parameter. Now we are moving towards the Bohr model. Bohr made some postulates for the correction of the by looking at the Rutherford model. Bohr suggested three postulates which can be used as a correcting model to the Bohr model, or the corrections to the Bohr model made by the corrections to the Rutherford model made by Bohr in the form of Bohr postulates. So now we are going to discuss the Bohr model, which has three postulates. The number one postulate is certain discrete orbits with a certain discrete value of the radius of the orbit represented by r as a subscript n Rn, with certain discrete energies En are allowed. So an atom has discrete energy levels. So the first postulate of the Bohr says that any value of orbit, any value of the radius of the orbit is not possible. The radius of the orbits that is the radius of the Bohr atomic orbit are discrete values, will take discrete values, and so the energy, the corresponding energies of the electron in the Bohr orbit will also be discrete, represented by the parameter n as a subscript with e. So En, because n will take integer values with both Rn and En. So since n will take integer values only, it means that the orbit, the discrete orbit Rn will not be a continuous parameter, and similarly the energy, the total energy of the Bohr or the total energy of the electron in the Bohr orbit will also be it will not be a continuous parameter but will be a discrete parameter. Okay, so this was the first postulate of the Bohr model. The second postulate is if an electron moves from a higher level means that is the level which is away from the nucleus, that having low binding energy, that is larger R value, and is moving from a higher level to a lower level, and the lower level means that is the level is closer to the nucleus, and when the electron is in an orbit closer to the nucleus, it will have a higher binding energy, and of course lower at a lower value of R. So at a larger value of R, the binding energy will be smaller, and for a lower value of R, the binding energy will be larger. So when the electron moves from a higher level to the lower level, it will emit radiation of a frequency nu according to this formula. So En minus En prime, that is the difference between the two binding energies of the electron between these two states, will be equal to h nu. And h is the Planck's constant. And nu is the energy, and nu is the frequency of the photon emitted during the process that the electron moves from the state n to the state n prime, where n is greater than n prime. And of course, r is also greater than r prime, because for a larger radius we have for a larger radius, the value of the quantum state parameter, that is the integer n, will be larger, and of course the radius will be also larger for such a state. Now from page number 8 of the previous slide, we have this expression given in equation number 10. That is, the wave number nu prime is equal to 1 over lambda is equal to Rydberg constant RH, and then multiplied within the parentheses we have 1 over n prime square minus 1 over n square. And there we found that n prime and n are integers. And it means that the nu that is the nu prime is not a continuous parameter but will depend upon these integer values. And if you multiply nu bar with hc, you will get you will get energy relationship. So you can use En prime, En minus En prime is equal to hc multiplied by nu bar. So nu bar, which is the wave number, if you multiply this wave number by hc parameter, which is constant, h is constant, c is constant, where c is the speed of light in vacuum, then of course you can also express the difference of energies using the parameter nu bar. That's the VM number. And a new bar from equation number 2.10 is substituted over here. And then you have HC multiplied by Rydberg constant RH, then multiplied by 1 over n prime square minus 1 over n square. So here you see that in the next step on the right hand side, I have dropped the subscript h with the parameter RH. That is with the Rydberg constant, because this relationship will now be applicable to all other atoms which are very similar to the hydrogen atoms. That is, which have a single electron outside the complete shell of the nucleus. That is, the electrons have completed shells and there is only one electron outside those shells. That is, the atoms are similar to the hydrogen atoms. For those atoms, this relationship will also be applicable. So that's why I have dropped the parameter h as a subscript h with the Rydberg constant, because this specifies that this is applicable only to the hydrogen atom. And now I have replaced it with the parameter h with the parameter r, which means that now this relationship will be applicable to all the atoms which are similar to the hydrogen atoms. And this is given on the right hand side of equation number 11. So En minus En prime will be equal to R times H times C times 1 over n prime square minus 1 over n square. So you see that equating the left hand side, that is En minus En prime, with these two terms on the right hand side, you can find out that En is equal to minus R times H times C divided by n square, and En prime is equal to minus R HC over n prime square. So you see that I have found the binding energies corresponding to the state n in equation number 12, and I have found the binding energy of the electron corresponding to the state n prime in equation number 13. So these two are the expressions for the binding energy of the electrons in state n and in state n prime respectively, in equations number 12 and equation number 13 respectively. Now you see that these binding energies depends upon, in the numerator you have constant terms. R is constant, H is constant, C is constant, and in the denominator you have the parameter n. And n will take discrete values 1, 2, 3, 4, and so on. It means that these energy expressions are the discrete energy expressions. So the binding energies over here of the electrons corresponding to different state of the electron will not be a continuous parameter, but will change discretely from one state to another state for the values of n. That's for n is equal to 1, n is equal to 2, n is equal to 3. So these values will give you the discrete values of the energies depending upon the discrete values of the quantum numbers n and n prime. So according to equation number 12 and equation number 13, the numerators contain constant terms and the denominators contain principal quantum numbers n and n prime. Thus, the energies given in these equations are quantized. So you see that Bohr has given you that the energy of the electron in orbits is quantized, not continuous parameter. That is, when the electron will jump from one state to another state, the energy will change in a quantized fashion, not in a continuous fashion as was suggested by the Rutherford. So you see that I have discussed the two postulates of the Bohr model. Now, looking at the Bohr model, we can compute different parameters. For example, we can compute an expression for the Rydberg constant, which we are going to do next. Bohr compared the orbital frequencies, which are given by, so nu, which is the orbital frequency, is equal to 1 over h multiplied by, within the parentheses we have En minus En prime. So this was obtained from equation 2.9. So let me show you equation 2.9 over here, and from here you have solved this equation for the value of the frequency, and then you have used this value over there. So the Bohr compared the orbital frequency given by this relationship with the frequencies of emitted or absorbed radiation to calculate the Rydberg constant R. Okay. Now consider the emission of light between neighboring distant. Here I am using neighboring and distant orbits n and n prime. So distant orbits mean that the value of n and n prime is much greater, because the distant orbits mean that the orbits exist at much larger distance away from the nucleus. So for that one, n and n prime are large quantities, but since they are the neighboring orbits, which means that their value, the difference of their values will be equal to 1. And I have set n minus n prime equal to tau equal to 1. So tau is a parameter that I am going to use next. Of course, the value of tau is 1, but this will help me to do the calculations. So now n and n prime are large values, but they are consecutive values. That is, the difference between the two values is equal to 1. And you know that n is greater than n prime. That's why n minus n prime is equal to 1. So using equation number 12 and equation number 13, in this expression, we have En minus En prime is equal to minus RHC over n square plus RHC over n prime square. So these are the values that I have used from equation number 2.13, and then the final result from equation number 2.9 is used, which is h nu. So En minus En prime is equal to h nu, and there in the middle I have substituted the values of En and En prime from equation number 12 and from equation number 13. Okay, now I am going to solve these equations. So from here you can get the value of nu over here, because the parameter h will be cancelled. On the rightmost side you have h, and in the middle terms you have a parameter h, which is the Planck's constant. You can cancel out the Planck's constants on the term on the right hand side, and then you have the frequency nu, which is equal to rc, which is r is the Rydberg constant, times c, times within the parentheses we have 1 over n prime square minus 1 over n square, and this n prime can be substituted with the value of tau. So from here you can solve this equation for the value of n prime. So n prime will be equal to n minus tau. So you have used the value, I have used the value of n prime substituted by its value, which is n minus tau squared. Now you see that you can take n square common from both these terms in the parenthesis, and then you can write rc over n square. Since you have taken n square common from these two terms in the parenthesis, then we have 1 over 1 minus tau over n, this whole term raised to power 2, and then minus 1. And then you see that you can bring this term in the numerator by putting the by setting minus 2 as the power. So 1 minus tau over n, this whole term raised to power minus 2, and then we have a minus 1. We can expand this term in the binomial series. So we have 1 plus 2 tau over n plus terms of the order of tau over n. Squared terms are will be rejected, because tau is 1 and n is very large quantity, and the square of that quantity will be much larger. So we are ignoring these terms. So we are keeping only the first two terms in the binomial series expansion of this term, which is 1 minus tau over n whole raised to power minus 2. So in the expansion of this one through binomial series, I am retaining only the first two terms, because the other terms are negligibly small. So 1 will be cancelled out with the 1, and then you see that we are left with the frequency nu will be equal to 2rc over n cube, which forms equation number 14, because here I have used tau is equal to 1. Now you can multiply equation number 14 on both sides by the parameter 2 pi, so that you can introduce angular frequency omega as shown in equation number 15. So omega is equal to 2 pi times 2rc over n cube. So you see that I have found an expression of the omega using Bohr's model. Now combining equation number 2.8 and 2.12 gives. So you see that what is equation number 12? This is equation number 12. And then we are using another equation, which is equation number 8. So let me show you equation number 8 over here. This is an expression of the total energy of the electron in equation number 2.8. So we are using equation number 2.8. And then we have this energy, which is the energy from the Bohr's atomic model, which is minus RHc over n square. This is the binding energy of the electron in the nth state from the Bohr's atomic model. And on this right hand side, which is the long expression, and this is the total energy of the electron using Rutherford model, because the this calculation also holds for the that is this expression of the total energy calculated using Bohr atomic model also holds for the using a Rutherford atomic model also holds for the Bohr's atomic model. So we are equating these two total energies expression. One obtained from equation number 2.8, the other obtained from equation number 2.12. That is from equation number 8 and from equation number 12. So let's take the cube root, or let's take the cube of both sides of this equation, so that we can introduce omega from equation number 15. That is from equation number 2.15. So after taking the cube of both sides, on the left hand side we have a minus r cube, h cube, c cube over n to the power 6, and in the is equal to minus 1 over 8, and then we have 1 over 16 pi square epsilon naught square, and then we have this term e to the power 4 m naught, and then we have left with omega square, and omega square value is substituted from using equation number 15, which is shown over here. So this is a term shown in the red is omega square. Now you see that here this value of omega square depends upon the value of r square also. So the r is given by, since r is equal to m naught e to the power 4 over 8 epsilon naught square h square over c from equation number 16. So you can solve this equation for the value of r, because here you have r cube on the left hand side, you have r square on the right hand side. So you can cancel r square with the r cube, you will left with one r on the left hand side, which is this r, and then moving all the other terms from the left to the right side, you are left with this expression, which is r is equal to m naught to the into e to the power 4 divided by 8 epsilon naught square h to the power 3, that is h cube, and multiplied by the speed of light. This is an expression for the Rydberg constant calculated using Bohr's atomic model, as shown in equation number 16. So the equation number 16 shows you the expression of the Rydberg constant obtained using the Bohr's atomic model. The classical value of omega found from equation number 2.3 is given below. So this is, you see that this expression gives you the classical value of omega, where omega is a continuous parameter. And this is what we have found from equation number 2.3, and equation number 2.3 is reproduced over here. So this omega was not consistent with the quantum value of omega found from over here. For small radius of orbit r. So you see that this is the value of omega that we have discussed earlier, that omega is equal to 2 pi nu, and here we have introduced the value of nu for using the second postulate of the Bohr's model. So we have omega is equal to 2 pi nu is equal to 2 pi, within the parenthesis we have en minus en prime divided by h. So this is the expression of the angular frequency omega, and you know that here the value of omega depends upon the discrete values of energies. So it means that omega, when through these discrete values, have a fixed value for a jump from the state En to the state En prime, and it will not be a continuous parameter. So the jump from the state n to the state n prime, when the electron takes this jump, then you see that it will emit a single frequency omega. And this omega will not be a continuous parameter, but will be only a single frequency. And you see that the expression given in equation number 17 holds for all values of n and for all values of r unless we reach the quantum region. Just before the quantum region, that is where n becomes so large that the levels are becomes so narrowly spaced that our instruments cannot recognize the separation between those very narrowly spaced levels. Under that condition, such states is called continuum states. And before the continuum states, we will be referring omega as the discrete values, because in the continuum region omega will still be discrete, but we cannot measure omega in such regions using our existing instruments. So far we have discussed two postulates of the Bohr atomic model, and using those two Bohr's atomic postulates, we have calculated also the expression of the Rydberg constant given in equation number 16. And we have also commented on the parameter of frequency omega, that is omega is also a discrete parameter and is not a continuous variable. So these are the two findings that we have are based on that is the energies are discrete. We have we have also found the expression for the Rydberg constant R given in equation number 16. And we also know from the theory of the Bohr's atomic model that the angular frequency, when the electron moves from one state to another state, it will emit a single frequency, not a continuous range of frequencies. And this frequency will depend upon the discrete energies, and the discrete energies depends upon the discrete quantum states of the electron. Now we are going to move towards the third postulate of the Bohr atomic model, given in the form of the correspondence principle. So the correspondence principle, Bohr postulated that with increasing orbital radius r, the laws of quantum atomic physics become identical with those of the classical physics. That is for very large values of r, that is for very large values of the quantum states, there will be a continuum of the continuum of energies will start. That is, the levels are so narrowly spaced that our instruments cannot differentiate between the levels, and the energies emitted when the transitions takes place between those narrowly spaced levels, we cannot measure though we cannot measure the frequencies emitted by such narrowly spaced levels through our existing instruments. So we call such a range or such levels as the continuum levels. And under the continuum levels, we can say that the quantum atomic physics become, that is the laws of the quantum atomic physics become identical with those of the classical physics in terms of the measure, as far as the measurements are concerned. So this is referred to as the correspondence principle, and this is also referred to as the third postulate of the Bohr's atomic model. In Bohr's model, the Rydberg constant RH is just the ionization energy of the ground state. N prime is equal to 1 of the hydrogen atom through scaling constant Hc. So you see that the Rydberg constant RH that we encounter frequently, this is actually the ionization energy of the ground state of the hydrogen atom. That is the hydrogen atom in the state N prime is equal to 1, and we provide energy to the hydrogen atom, just enough energy that the hydrogen atom is ionized. That energy will correspond to the Rydberg constant RH. So if we multiply the Rydberg constant RH with the scaling factor Hc, we will get that amount of energy that is that will be minimum sufficient energy required to ionize the electron in the hydrogen atom when it exists in the state N prime is equal to 1. That is the ground state of the hydrogen atom. So you have Rydberg constant RH, multiply it with the parameter Hc, where H is the Planck's constant, C is the speed of light in vacuum, then you will get an energy which will be sufficient to raise the electron from the ground state of the hydrogen to the ionization state. And you know that the ionization state can be represented for the quantum state to be equal to infinity, because beyond the ionization no levels exist, because the atom is ionized, the electron is free now. So you see that we have expressed this difference of energies of the binding energies between the state n and n prime to be equal to hc times rh and times within the parentheses 1 over n prime square minus 1 over n square. So actually new number has been, that is the, before that we were using the new wave number, and now we are representing this in terms of the parameters hc and rh. So you see that now we try to manipulate this equation in order to find in order to find some useful information. So setting n prime is equal to 1, that is the hydrogen atom is in the ground state, and setting n goes to infinity, that is we want that the hydrogen atom should leave the atom, that is the atom becomes ionized, and the electron in the hydrogen atom should be ionized or should leave the atom by setting n goes to infinity. We are changing RH by the value R infinity. So R infinity is actually the same value of RH, but we are putting a subscript infinity in the sense that this means that we are calculating, we are raising the electron from its ground state n is equal to 1 to the state when n is equal to infinity. So the difference of energy, which is E infinity minus E1, that is the difference of energies between the state when and the electron, when the electron has ionized, and the difference of energy with the electron when the electron is in the state 1. So E infinity minus E1 experimentally found the value of this one is equal to 13.59 electron volt. So if you give this much energy, 13.59 electron volt to a hydrogen atom in the ground state, the electron will be ionized. So that's why we have set E infinity minus E1 to be nearly equal to 13.59 electron volt, which is the ionization energy of the hydrogen atom, where 1 electron volt is equal to 8059.44 centimeter inverse. And this value has been worked out on page number 9 of the slide number 1. H is the Planck's constant with a value of 6.62607015 into 10 to the power minus 34 joule second. C is the velocity of light in vacuum, which has a value close to 3 into 10 to the power 10 centimeter per second. And 1 joule is equal to 6.242 into 10 to the power 18 electron volt. And solving the equation for R infinity, that is we are solving equation number 11 for the value of R infinity, you will find this value using the data given in the paragraph, that R infinity will be equal to 109737.318 plus minus 0.012 as a tolerance, and this value is given in centimeter inverse. So equation number 18 gives you the value of the Rydberg constant in centimeter inverse. This is an experimentally measured value and inferred from the experimentally measured ionization energy of the hydrogen atom. The empirical value of RH, that is the Rydberg constant, given on page number 6 of the slide number 1 is given. RH is equal to 4 over G. And you know that G is the constant that was introduced in the Balmer formula by the Balmer. Balmer introduced first this constant in its empirical formula. So we have the Rydberg constant RH is equal to 4 over capital G. And if you substitute the value of G from the Balmer formula, you will find this expression, which is 109677.5810 centimeter inverse, as shown in equation number 19. So we have two values of the Rydberg constant, one obtained experimentally, which is given in equation number 18 using the ionization energy of the hydrogen atom, and the other one is obtained numerically or empirically using the constant G of the Balmer series formula. So we have RH, we have two values of RH. That is the Rydberg constant, and you can see that there is a small difference between the two values. Now the empirical value of RH can also be obtained using equation number 16, which is reproduced below. So you see that we have obtained this formula from using Bohr's atomic model, and the value of Rydberg constant using Bohr's atomic model is equal to R is equal to m naught e to the power 4 divided by 8 epsilon naught square h to the power 3 multiplied by c. And this has been shown also in equation number 16. So putting the value of these one, that is the mass of the electron, the charge of the electron, the Planck's constant, and the speed of light, you can also obtain a numerical value using this numerical value of the Rydberg constant using this expression. The total binding energy of the electron in a hydrogen atom when it is in the nth atomic when it is in the nth quantum state is given by equation number 12, which is reproduced below. So you see that this is binding energy of the electron in a hydrogen atom when it is in the nth quantum state is En is equal to minus RHc over n square, and this is also shown in equation number 12. The total binding energy is also given by equation number 2.7a, which is also reproduced below. So we have also obtained an expression of the total energy of the electron in equation number 2.7a, which is reproduced below. So En is equal to minus half times E square over 4 pi epsilon naught times Rn. So you see that you can equate these two expressions of energies, and then you come out with this expression. So you see that in this expression, we want to solve this equation for the value of Rn. So we are solving this for the value of Rn, and the rest of the parameters are on the right hand side. So we have Rn is equal to n square E square divided by 8 pi epsilon naught into capital R into H and C, where R is the Rydberg constant. So again, using the value of R from equation number 16, which is shown in the red over here, because 1 over R, the value of 1 over R is shown in the red over here, we have this expression. Now, simplifying this expression, we have this expression for the value of Rn. So Rn is equal to n square h square into epsilon naught divided by pi into m naught into E square. So here you can see that all terms are constant except n. So the value of Rn depends upon the quantum variable n, or the quantum number n. So the square, so Rn depends on the square of the quantum number n. So the n takes discrete values, so it means that Rn will also take discrete values. That is all values, that is according to the Bohr model, the electron orbit Rn will only take discrete values. And we can also express this equation using the reduced Planck's constant, which is h bar is equal to h over 2 pi. So introducing h bar is equal to h over 2 pi, this expression, that is the Rn value, becomes equal to Rn is equal to 4 pi times epsilon naught times n square h bar square over m naught into E square. So this is equation number 20, which gives you the value of Rn. And again, you can see that all parameters, that is h bar square is a fixed parameter, or m naught fixed parameter, charge of electron is a fixed parameter, epsilon naught is a fixed parameter, and it means that the value of Rn depends upon the square of the quantum number n, the principal quantum number n. So it means that Rn will take only discrete values. So according to the Rutherford model, the radius of the orbit will be a continuous parameter, but according to the Bohr's atomic model, Rn, that is the radius of the orbit, will only take discrete values. So you see that this is what equation number 20, that is the discrete, that is the expression of the discrete values of the radius of the electron orbit has been obtained using Bohr's atomic model. It is obvious that the value of Rn depends on the principal quantum number n, and that Rn will acquire only discrete values. That is, only discrete orbits are allowed. Now you see that we also, next we want to calculate the orbital angular momentum using the Bohr atomic model. The orbital angular momentum of an electron is given by L is equal to R cross P, where R is the radius of the orbit, P is the momentum of the electron in that orbit, and L small l is the orbital angular momentum of the electron. So here in the next we are going to take the magnitudes of these quantities. So the mod of L is equal to the mod of R cross P. And here, since R in the Bohr's model is represented by the discrete value Rn, and the momentum P will also be discrete because the velocity it depends upon m0 times v, and v will also be a discrete quantity. So we have, since we have taken the mod over here, so we can when we omit the mod, we have the quantities m0 Rn times Vn. So there is a subscript n with the R quantity and the subscript n with the velocity v. It means that Rn and Vn are both discrete quantities. So Vn will be replaced by Rn times omega n, because you see that's why we put the value of Vn to be a discrete quantity, because Vn depends upon the value of Rn and omega n. And previously we have established that Rn is a discrete quantity, and we have also established that omega n is also a discrete quantity. That is why before going into the detail, we have initially put the value, put the subscript n to v, so that we can indicate that n would also be a discrete quantities. So using Rn from equation number 20 and omega n from equation number 15, we can write these expressions over here. So you see that we have m0 over here, and then we have Rn square. So this is the value of Rn raised to the power square over here, and this is omega n. This is the value of omega n, and this quantity in the square is the value of Rn taken from equation number 20, and this value of omega is taken from equation 15. So here you see that we have the value of R also. We have R parameter R. This is the Rydberg constant is also present over here on the right hand side, and we can use the value of R using equation number 16. So we have also substituted at the last point on the rightmost side the value of capital R, which is m0 e to the power 4 divided by 8 epsilon square h cube and c. So this is the value of omega, and this value of omega is substituted using equation number 16. So having substituted all these values, that is the value of Rn square, the value of omega n, and the value of R, I have written this expression in the following form with the different colors. This is the same expression but with the different colors. The only difference is that I have from this term, which is a squared term, I have taken n and h bar outside this parenthesis. You can see over here that L mod is equal to n h bar. This is n h bar. I have separated it from the rest of the quantities. And the other quantities, I have expanded them. That is, I have taken the square of this quantity over here. And now I have marked the different quantities with the different colors. For example, m0 is shown in red, and within the parenthesis we have m0 square, and then with the term on the Rydberg constant we have m0 again shown in red, so that we can show the cancellation process. So m0 will be cancelled out. We have shown epsilon naught square and also epsilon square over here in the denominator, so epsilon square will also be cancelled out. And C has also been shown, so C will also be cancelled out. And the quantities and E square, which is e to the power 4, is shown in green. This will also be cancelled out. And then you see that finally, after cancellation of common terms, we have this term, that is the orbital angular momentum will then is now equal to nh bar, and then with the first parenthesis contain 16 pi square into h cube, h to the power 3 divided by 1, 2 pi times 2 over 1, and then the last parenthesis contains 1 over 8 h square. So you see that in the next slide I have given different colors to these parameters, And you will see that all these parameters will be cancelled out, and all the parentheses will mutually cancel out each other, and then we have the mod of the orbital angular momentum of the electron will be equal to nh bar. You see that h bar is a constant quantity. It means that the angular momentum, the orbital angular momentum of the electron is also a discrete quantity and depends upon the principal quantum number n of the system, where n will take values n equal to 1, 2, 3, and so on, as shown in equation number 22. So here I have established that the orbital angular momentum of the electron is also a discrete quantity. That is, the orbital angular momentum of the electron is quantized, that this is incorrectly taken as the Bohr's postulate. So you see that this is not the Bohr's postulate. And some books are writing that this is the Bohr's postulate. This is incorrectly taken as the Bohr's postulate. This is what we have derived using the Bohr's model. Bohr model does not discuss the electron's behavior as a function of time. You see that this is one of the drawbacks of the Bohr's model. That is, we have no time involvement in these calculations. That is, the Bohr's model does not discuss electrons' behavior as a function of time, but only its stationary initial and final states have been discussed. At normal temperatures, where n is equal to 1, the state is the n is equal to 1 state, that is at normal temperature n is equal to 1 state is occupied by the hydrogen atoms. So only the Lyman series in hydrogen atom is observable in absorption spectrum. When we measure the stellar data coming out from the stellar using absorption instruments, absorption spectrometers, we will only observe the Lyman series at normal temperatures. When the Balmer lines are observed in the spectra of stars as Fraunhofer lines, that is, missing lines in the continuous spectra due to absorption of light on the way through stellar atmosphere, the first excited state of the hydrogen atom, the first excited state of the hydrogen atom in n is equal to 2 is also occupied. So you see that in the stellar objects, the temperature is high enough that the atomic hydrogen is also observed in the second state. That is n is equal to 2 state is hydrogen in its atomic state is found in its n is equal to 2 state around the stellar objects due to very high temperature. And the light emitted by such hydrogen atoms will produce a Balmer series, which we have discussed in detail in previous slide. So you see that the temperature will raise the hydrogen atom, can raise the hydrogen atom in the higher states depending upon the value of temperature. So this is the basis of spectroscopic temperature determination using a Boltzmann distribution. So the fact is that one hydrogen atom out of 10 to the power 8 hydrogen atoms in solar atmosphere are in the n is equal to 2 state. So 1 out of 10 to the power 8 in the solar atmosphere will be are found in the n is equal to 2 state. So you see that I have discussed the Rutherford model, I have discussed the Bohr's atomic model, I have discussed the calculation of different parameters, that is the parameters of the Rydberg constant, the parameter related with the atomic orbit, with the atomic radius of the electron in the hydrogen atom, the discrete concepts of energies, the discrete values of the atomic radius of the electron in the hydrogen atom, the discrete values of the orbital angular momentum of the electron in the hydrogen atom. These three parameters have been derived using Bohr's atomic model. So this is the end of slide number 2 of the course on atomic and molecular physics.